Thanks to Dr. Gracie for inviting me, and thanks to Connections. I don't know how I'm going to speak after Paul, because he had me taking notes, which I normally don't do when I go to these events. I just listen, but I was taking notes. And I kind of disagree with him on a couple of things, which he and I will take offline. But it's nice to be here. Thanks for the opportunity. Just before I get into my presentation, just a little bit of our background, who I am. So, Lawrence Jones. Education is kind of funny because I was actually born in Liberia. I went to school in Liberia where, as you were saying, we didn't have any computers. We had no microscopes. We basically were learning the fundamentals. But the thing we did have was observation. So we used to go out and just observe nature because we didn't have laboratories. And growing up, I wanted to be a vet. So the biomimicry thing is something I spent the first 9 years of my life experimenting about how to be a vet. My parents wasted their money on me because I had my own little zoo at home, had all kinds of animals, rodents and snakes, and I used to put them in glass and observe them. And then I went to high school, and then in the 8th grade, I got a C in biology. And in my father's house, or my parents' house, there was a rule that any C meant no Christmas presents, and a D meant no summer camp, and an F meant you were thrown out of the house, basically. And so I came home I went to a boarding school, came home very frustrated. I had gotten a C. I figured I'm not going to get a Christmas present, so I decided to go out and open all the cages and let all the animals go away. My mom came home and said, "What happened?" And I was there crying and sobbing. She said, "Well, we didn't really mean it that way." So that ended my biology interest in being a vet. And then I left Liberia when I was after high school, 2 years after high school, and I went to Sweden. So it's sort of a contrast going from learning where you just learn the fundamentals to now learning where you had access to everything imaginable in the world in terms of technology, in terms of computer science. I mean, you just had everything you needed there. We took the learning to a next level, except that I had to learn Swedish, which took a year, but that's a different story. The interesting thing here is that the fundamentals were there. And people ask me how I made it when I went to Sweden is because all of the other tools that you get afterwards, the computers, the microscopes, and all that stuff, it really doesn't make any difference if you don't have the fundamentals. And as even now my Swedish professors try to lay claim to me as educated in Sweden, I tend to remind them that I was only educated in Sweden because I had the fundamentals from Liberia, which was where I got my exposure to education and that observation. And then I moved to the States. I actually never went to school in the States. So I did my PhD in Sweden. And when I moved to the States, I got involved with university. I was first in Seattle. I was still working for Alstom. I never worked for the university, but I was always some sort of an adjunct professor because I always had this love for teaching, this love for helping the next generation to get involved. And so I joined Alstom now as an engineer and doing a lot of work around the world. And then 7 years into my career in Alstom, my then boss said, "Look, we need someone in DC to explain these technical issues and concepts to policymakers and regulators." So I moved to DC, and I remember my very first meeting in DC. I was at the Federal Energy Regulatory Commission, where you sit with regulators who decide the fate of the energy industry. And I went to give them a presentation to the commissioners on some complex optimization theory. And I went there with my boss at the time, and I was up to present, young person in my career. I get to the board, and I had this fantastic presentation, I thought, because it had every sophisticated optimization concept in the world, equations. I was fired up. And these 6, 7, 8 folks in the room just sat quietly looking at me with a stare. And I just kept on going. I talked about, mixed optimization. I mean, I brought every theoretical concept I knew because that was it. We're done. The chairman said, "Thank you for coming." My boss and I were leaving the room. He turned to me and he said, "We'll never do it again." Bailey, that was a great presentation. He said, "Those people never remember anything you said. because you were way above their head. I said, wow. He said, you have to change your language if you're going to be successful in DC. So I spent the last couple of years in DC trying to not be an engineer, which is not an easy thing if you've become an engineer, right? You're stuck in your way of thinking. So I tried a lot of things to not be an engineer. So I say that to say, for me, when I was asked, I met Dr. Bracy and Phoebe to come and have this conversation, often I go with my daughter to her school and I speak to her class. She's now in the 2nd grade. I've spoken to her 1st grade class. And the first presentation I did with them was on solar energy, because my research is on energy and energy systems. And I remember this young kid in her class who, now this is right after we had dropped the bomb in Afghanistan, the mother of all bombs, right? And I'm talking about energy systems, and this kid raises and says, I have a question. He said, why don't we just drop more bombs and capture all the energy? What do you say to a group of 20-year-olds when the guy in the back is suggesting that we drop more bombs because for some reason his father worked at NASA and he'd figure out that bomb has energy?
Did they drop us again?
And they,
hear us now?
she heard drop bombs and she tried dropped her. No, but coming back to what you said, Paul, when you talked about what we learned from outside,
Can you put your side on mute, please?
right? The kids were learning stuff. For this kid to make the connection between dropping bombs, he was actually right. Bombs have a lot of energy. But the context in which he said it, dropping a bomb in Afghanistan, he didn't realize what that dropping of that bomb did. But his context was it's a cool thing to do because it generates energy. Right? So just coming back to what you said, in terms of how we learn from society, we got all these different signals that are coming in. So you said a lot of things I was going to say. People will think that you and I were synchronized when they see my presentation because I'm going to use slides that will remind of what you said. Yeah, this is my first time meeting you, so this is not a choreographed thing. Dr. Brace didn't do that. So I will skip over some of the slides that come back to what you talked about. But I call my presentation Solving Problems That Matter. Critical Insights for Preparing the Next Generation of Engineers. I gave a version of this presentation 3 years ago. It was a webinar. We had 600 participants on the webinar. It was done by Elsevier, the publishing company from around the world. So I couldn't see who was in the room, but I got a lot of questions. And so I sort of built upon this theme for this presentation. Just see if it works. It should work. Move. Shoot. There we go. So, okay. So basically, I'm with the Edison Electric Institute. We're not an educational institute. We're a trade association that work with utilities around the world, mainly energy companies around the world. I run the international program. We focus on public policy, technology, best practices, business ideas, investments, attracting finance to the industry. But it's all about electrifying the world. I mean, that's basically what we try to do. Edison, because of Thomas Edison, he obviously knew what he did. The international program, we have about 70 international members in 90 countries. And so getting me to be in DC or in the States is a very rare thing, but because I'm on the road quite a bit. So, you know, Paul talked about imagining the future we want. And so imagine a day in your life in 2020 or 2025, or pick a date you want, right? And the question is, what is that day going to look like? You know, what are the problems you're going to be dealing with on that day when you wake up? If this is, you know, June 21st, 2020, you know, what are the problems you're going to have to be grappling with as a person, as a society, as a community? Because again, engineers are supposed to solve problems, right? In theory. One thing I think what's going to happen is that for sure we think everything will be smarter, right? But the question is, will we be dumber? Because as things get smarter, there's a tendency for us to rely on things and less on us and less on people. And so from an engineering perspective, you ask yourself, so what is engineering in the context of if things are getting dumber and everything was getting smarter, but we were getting dumber, you ask yourself, so what is engineering? So this is a quick quiz I did with the audience of 600 people. I didn't see who they were, but I can see who you are, so I can sort of sample your response. So how many people think engineering is a science? 1, 2, 3. And art? 1, 2. Okay, both. Okay, none of the above. Had to be somebody odd. Perfect. I think you just did it to vote, right? But it's both. And the interesting thing is, for a long time, engineering has been seen as a science. So STEM originally, that's now called STEAM, and maybe it'll be called STEAM when we add the sustainability to it. It's evolving, right? And so what is engineering? And there's so many definitions. This is the one I like the most, simply because it is all-encompassing. So I'll just read it. Field of discipline, practice, profession in an art that relates to the development, acquisition, and application of technical, scientific, mathematical knowledge about the understanding, design, development, invention, innovation, use of materials, machines, structures, systems, and processes for specific purposes. A long definition, but it captures everything. Sadly, most of the engineering education I have encountered doesn't even come close to reflecting this definition, because it's siloed into one small piece. So engineers, what did they do in the past? What do they do today? And what will they do tomorrow? Right? So the whole idea of MESA and all these STEM programs is to prepare engineers to do stuff in the future. But the first question to ask is, what are they doing now? And what will they do in the future? How do you envision what they're going to do? I say the problem of what engineering is and what they're doing is a little complex. And I try to put it in 3 dimensions. Scale, and you will see why I say scale matters. Complexity, and speed. And if you think about it from a math, engineering, science perspective, these are 3 words that have basically been affecting engineering for generations. Right? So engineers build things. They build big things. They build simple things. They build complex things. They build small things. And you can see an example here from the Hoover Dam. You have the Google device for sensing. You have the Eiffel Tower. You have the Boeing. Well, that's not Boeing. That's Airbus. But since I'm in the States, I'll say Boeing. So you have Boeing, and you have the pyramid. I mean, think the pyramid. Engineering feat. To this day, we haven't been able to really design a convection system for cooling buildings. And I keep telling, go to the pyramid. I mean, think of how they came about all this stuff, right? So engineers are great at building things. And the question is, even in the context of what Paul talked about, sustainability, how are you going to be building things when you're dealing with this notion of sustainability? Is there a link? Is there a challenge, right? And so the reason why I said problems or solving problems that matter is because engineering fundamentally is about solving problems, building things to solve problems. What is happening now is engineering is more and more becoming building things and then looking for problems. In the old days, people will know there's a problem to solve, and then will build something to solve this specific problem. Now, because of technology, the pace of developing technology, people then develop the technology and then start looking for the problem. And like Einstein said, I'd rather spend 99% of my time understanding the problem and just 1% of my time solving it. We've reversed it now. So we train students to spend a lot of time building something without understanding the problem it's going to solve. So if you look at most engineering textbooks, they start by telling you all the different applications, the different solutions, but spend very little time on what problems they're going to solve. Not the engineering problems at the back of the book where you say, well, solve these problems. The book always starts with all the theory and then solve the problem. What if you reverse it? You put all the problems up front before you get into the solutions or the analytical approaches to solving the problem. Because most textbooks have problems at the end of each chapter. Why not put the problems at the beginning of the chapter? Right? So the problems that matter, and Paul talked about climate change, energy poverty, water poverty. How do you feed 10 billion people? I mean, we're not 10 billion in the year 2050, but we'll be close. We will probably be around 9. So how do you do that? right, in terms of solving problems. And so if you take energy poverty, this chart, or this diagram shows the world at night. It's a sort of a, not 100% accurate, but it's a very good depiction that NASA have been generating. And I've been, plotting this, or downloading it every year now for the last couple of years. And what has happened is most of Africa is beginning to get illuminated. But imagine if the rest of the world got as lit up as the US. Just imagine how much energy it's going to take to light up Africa and to light up Asia with the same intensity as it is for the US. Just imagine the challenge. I mean, there are a lot of opportunities, but just imagine, how do you solve the problem of being able to electrify Africa? Not to mention, how do you hydrate Africa? Or how do you hydrate Arizona? Or how do you hydrate Cape Town in South Africa? So these challenges are all very, very much interrelated. Another thing that's, from an engineering perspective, I find fascinating is urbanization, how we live. What I find so fundamentally flawed with the human mind is that we have a planet that is full of land, but we are so dumb that we decided to all live on the coast. We've lived on the coast, and we are now believing that urbanization, the more we can live in these compact spaces, is the most efficient way. But is it the most sustainable way? Because we know that diseases spread quickly when you have congested areas. We know that traffic pollution go up when you have congested areas. Yet and still, the economists will tell you that living in the city is the best way because of economies of scale. But is it really the situation? Because when you think of urbanization and population growth, you're asking yourself, think about Philly. What is Philly going to look like in the year 2020 or 2050? Where else are you going to drive? Where would you have buildings? I mean, in Washington, D.C., when I moved there about 8-9 years ago, you had vacant lots all over the place. Now they're all gone. Buildings and high rises, to the point where you may not even be able to see the sky any longer. But somehow, that is what's driving development around the world. So the Sustainable Development Goals that Paul talked about, one of the things, that looked at smart citizen urbanization. My challenge with urbanization is that it's sucking people into these clusters, creating a food security problem because no one is growing food anymore. And so you now have this issue of a lot of these metropolitans around the world, the mega cities like Lagos, Sao Paulo. Pretty soon you would even consider New York, or who knows, even Washington could be a mega city given the size of Washington and the population density in Washington. So why are we doing this? Now, I'm bringing this up because in terms of the problems that engineers need to solve, it's going to be more about building things that are physical. It's also going to be about building things that are practical, things that are sustainable, and things that will require us to understand the risk of things like cybersecurity as we become more and more interconnected. What is amazing is that we're so more vulnerable now, but no one wants to talk about it. Yet and still, we're still urbanizing and urbanizing. And one city to visit, if you ever have the opportunity, is to visit Copenhagen. In the morning, 7 o'clock, you see almost 600,000 bicycles. I'm not kidding, the entire city. Everyone is biking. It's like a swarm of bikes coming. Everyone from the prime minister, who name it, everyone's going to work. It's a natural thing. It's like he said, people have now adapted that lifestyle. So when you get there, guess what you end up doing? If you're a tourist, you rent a bike. Because taxi, the cost is so high, you don't want to ride a taxi. And the bikes are so cool now, they have bikes that have wheels that actually measure the pollution in the air and send that information back to some centralized database that tells you that by the more you bike, the cleaner air you generate. So all of these kinds of things, from an engineering perspective, the problems to solve are there. So this brings me into a class of problems that engineers for a long time haven't been looking at. And this is where I think the notion of systems thinking, and where I think educating young people to realize that there's no reason to not tell them about the complexity of the world in which they live. We seem to be fearful. I've heard engineering professors and educators say, well, they're 8-year-old, they're 10, you can't expose them to all these complex problems. Well, I'm sorry, my daughter is 8, and try engaging her in a complex problem and you will lose. Because these kids have a whole different receptivity to understanding complexity than we think. And so if you look at the whole class of problems now called wicked problems, these are problems that have no easy solution. They're complex. There's no equation to solve them. Like if you take climate change, there's not one way to fix it. If you take extreme poverty, so they're so interrelated. So the old engineering problem-solving approach was to have a problem, look at Newton's equations, or look at Einstein's E equals mc squared, write an equation, come up with a solution, design it, you're done. Now, with these so-called wicked problems, there's no easy engineering solution. So how do you educate a young student to start thinking in terms of, yes, you're solving this particular problem, but remember that there are all these other ancillary problems around it that you have to think about. It poses a lot of stress on teachers, actually, because I know we talk about how do we, and I have a slide about what we do about the teaching. The teachers themselves need to start thinking differently to be able to educate the students, right? And that's where the challenge is. So what are some of the trends that will shape, from an energy perspective, when we see the energy industry, when we look at organizations like MESA, and we look at other STEM programs, what do we look for that we think is attractive, both domestically and internationally, before we decide, let's support XYZ program? We look for some of these trends, and we look for organizations that are not just duplicating what has been done, but who are actually catching on with the trends, because the engineers we want are engineers who are following these trends and being able to respond. So take something like 3D printing. When I was going to school in Liberia, I was great at mathematics. I could describe anything analytically, but if you put me in the lab and gave me a hammer, I would nail my finger, because I had no real feel. I didn't have the physical experience. What 3D printing is doing for education is fascinating. Now, you don't just design something in the abstract. You can actually print it out and look at the physical object. Imagine what that does for a kid who designed a car or design a robot. We used to do these experiments where you would design a robot, you write the equation and you design it, and you know that if you do your propulsion is going to fly out of there, all this stuff. But you never actually saw a real robot. You never actually saw a plane. Now imagine a kid being able to design using a 3D printer, something he can touch and feel and go back home and say, look, I did this. So 3D printing is going to really transform it. The other thing is material science. Material science is so fascinating because, I love your example, Paul, about the spider, because when we look at material and the strength of materials, this is an area where I think organizations like MESA and others who are getting more and more involved in engineering should tie engineering and material science together. Because right now there's a disconnect. Engineers are still living in this, especially like energy system engineers or mechanical engineers. Back in the day, we had this course called Strength of Materials, which we all had to do. Well, it basically was the precursor to material science. But there are so many new materials that are popping up: graphite, silicon. Those things were not there before. There's no reason why you can't expose students to what I call the new periodical table, because the old one is past. The new one now has more material. So if you're a student coming out today and you don't know what silicon carbide is, but you know exactly what, you can tell me about hydrogen and whatnot. I'm not concerned about hydrogen. I want to make sure you understand what graphene is. I want to make sure you understand what silicon carbide is, and some of these new types of materials that are coming out. So the other thing is that everything is becoming integrated. I talk about the hyper-integration and convergence. If you think of the city, you have water systems, energy systems, transportation systems. They're all coming together. Now, that means educating an engineer, when I'm building a road, I have to realize that if I put a conduit here for a sewer, I could use that same conduit for a power line. I could use it for a fiber optic cable. So multi-purpose use of engineering infrastructures requires engineering students to start, I'm not just doing electrical engineering, I'm doing electrical engineering to be able to integrate with chemical engineering or mechanical engineering So if you look at how the engineering schools are structured, there's where you have the first problem. And Dr. Brace is about to kick me out of here. Because I'm about to say, because why do you have School of Mechanical Engineering, School of Bioengineering, School of this engineering? Why do we have all of these silos? Just have School of Engineering. And if I were a professor or a president of a university, I will make the head of the mechanical engineering department work there for 2 years and then transfer over becoming the head of the biomedical engineering department. Because at the end of the day, it doesn't matter. If you understand the fundamentals, you can apply it different places if you're at a certain level. But we create all these silos and then expect the students to come out and be able to think, I went to the engineering school. I remember in Sweden we had the School of Chemical Engineering. 99% of the students were girls. They were women. Electrical engineering. 99% of us were guys. So we struggled finding girlfriends. So we had to like crisscross over departments, not to learn, but just to find girlfriends, right? Imagine how easy it would be if they just created a school of engineering that had the students learn different aspects of engineering instead of creating the silos. I know the silos are done for more political reasons. Convergence. The iPhone. So fascinating. Most people think that the iPhone is cool. The iPhone is the best thing that ever happened. Best innovation. Okay, so in the energy system, the transmission lines, these long towers most people see they don't like, there's something called a transformer. The big ones have 765 kilovolts, right? The amount of innovation that has to go into designing that thing makes iPhone look like nothing. Because you have to test it, you have to test the material, you have to do all these different mechanical tests, electrical tests, before you put it onto the grid. Today, my friend here and my daughter can get together, develop an app. She will develop the app. He may tell her what he wants, because she's better at app development. She'll develop the app. In less than a day, we'll have the app on the Apple Store. There is nothing innovative in that. I'm sorry. And this is where my friends at Apple say I'm just trying to beat on them. There's nothing. True innovation is that the problem that transformer is solving is more relevant for the sustainability of the planet. The problem is Wall Street, society values this app more than the value that transformer. That's where I think we have a big problem, is that there's a disconnect between what's the value of engineering and what is the value of developing these apps. So the fact that Uber is worth like $100 billion, but a utility like Exelon is worth only $30 billion, but Exelon is the one that keeps the lights on, just tells us the issue you bring up of sustainability. That's the challenge we're going to have, right? So convergence is great, but it's affecting our values, mindset in terms of what we place value on as a society. The other thing I find fascinating is what I call the commoditization of skills. What is happening is when you treat an engineer today, he is not competing with just his peers in the US. He's competing with 100,000 other engineers around the world. So that means he has to stand out like that fish in that swarm of other fish. So you got hundreds of thousands of engineers every year. How is a MESA student going to compete with a student of science and engineering from Beijing, or one from Melbourne, Australia, or one from Russia, or one from Nigeria? So, and because the global community is now looking at skills from a global standpoint, today was a sad news for America. Every American today should be crying. Every American. If you believe in technology, if you believe in American ingenuity. Why? Because yesterday, General Electric was taken off the stock market. Think about it. General Electric was kicked off the Dow Stock Exchange and replaced by Walmart. Now, people think this is, it's just global competition, There's a huge implication what that means for science and engineering in America. Because GE was one of the biggest supporters of STEM programs around the country. They're one of the biggest supporters of a lot of things that students did, because GE was where most American students ran to. GE, whatever you liked, did a lot of good for America. But what happened? GE managers said, let's go global, which is great, but let's also divest. Let's invest in this, and let's get more into apps. We had this new, software. So what happened is the fundamentals of making things, we went away from it to some extent. Who's catching up? Korea, China, Japan, Turkey. These countries now make the very thing that made GE great. And so when I say it, having worked for Alstom and ABB and these companies, is that the skill is being commoditized. So it doesn't matter where you sit now. So your students have to be able to think global, not in terms of traveling abroad, but who's going to be competing with me? And how is it possible that the Chinese, after 20 years, can build a 765 kV substation by looking at what GE has done? And today, very few American universities are training engineers to produce those 765 kV substations. The best university in China is called the Tsinghua University. Tsinghua is called the MIT of China. I visited them last year. Talking to one of the professors, he said to me, "Lawrence, do you know who goes to MIT?" I said, "Who?" Make it into Tsinghua. Think about it. So the students who do not merit to enter Tsinghua University, the second-tier students, are the ones who go to MIT as first-tier students. Those students at Tsinghua University, their lunchroom, above in second level, third floor is where the dining room is. The second floor is where the professors have their dining room. And so I asked the professor, "Can we go upstairs and eat?" No. Those students' food are paid for by the government. It's the best food. We have to eat there. We have to pay to be in their dining room. Their food is served with the best of beef. And if they flunk or they fail, they're not only penalized, their parents are also penalized. Now, the point being, the emphasis on education is so much so that they will give you free food, but you have to deliver. Talk about giving free education in America, everybody freaks out. Well, China is giving their top students free science engineering education because they know that's the foundation. To get a very top education in America, as a science student, you have to pay. Your parents have to pay $40,000, $50,000 a year. Something wrong with that connection. So the commoditization of skills is something we need to think about. So computing is everywhere. We now have computers all over the place. Your iPhones here, everyone has iPhones, right? And we think it's all great, which is fine. But from an engineering perspective, what do I do? Artificial intelligence. The next thing that every engineering student is thinking about right now. But what do I do with it? What does it mean that I now have this thing called artificial intelligence? Well, I can tell you, China is bent on dominating this space. How many engineering schools in America have a program on artificial intelligence? Probably, huh? A lot now, but the question is, why are they teaching? I know, but what are they teaching in the program? They may have the program, you're correct, but the content of the program is tilted not to using artificial intelligence to make stuff. It's back to developing app. So we've become, you call it a consumer society. It's all about the app now. It's not about making things, right? And so you have more people going into the sciences, not to make stuff, but the quick way out is to do an app, right? And that's the challenge we're going to face. And from a corporate standpoint, one of the challenges we face as an industry is that we're looking for engineering students who are not just building apps, but who can also think about the physics, the physical world. And so when I interview candidates to come and work at EEI, I don't even look at their grades from school because I know it's going to be the top class, right? I start asking them, so how often do you spend time in nature? And the moment they tell me no, I know that, okay, I don't need this guy on my team. Because if you're not spending time in the environment, understanding nature, if you're all just sitting behind the computer typing, you're not developing your mind. You're not developing your thinking capacity. So how do we prepare the students from an engineering perspective? This quote from Descartes: "To arrive at the truth once in your life, You have to commit yourself to undoing all the opinions that you have formerly taken for granted and reconstruct new systems. Paul talked about paradigm shift. There has to be a paradigm shift in engineering. And I think for organizations like MESA to really sort of get the attraction from energy companies, that think of yourself as that yellow fish with all those blue fish. How do you become a yellow fish? Because there are so many organizations coming with all kinds of ideas, and they're all good ones. But I think finding a way to be the yellow fish as an organization in terms of what your students are doing that makes them unique is where I think the focus needs to be. So we need new paradigms, right? How do we educate engineers? The content has to change. The structure of the engineering has to change. The tools have to change. The curriculum, a lot of interdisciplinary discussions. Everyone says we have an interdisciplinary educational system. And when you realize what it means there, you see that it's really not interdisciplinary. They have the students maybe taking courses all over the place, but their instructors they don't come together. So for me, an interdisciplinary course is one where a professor from sociology sits with a professor from history and a professor from engineering, together deliver the message to the students. That coming together from an educational standpoint at the teacher's level, I think, is very key. Experimentation and prototyping, that's where 3D comes in, allowing you to quickly do the experiment, prototype, and have you come home with something cool. Kids want something cool. Engineering is boring for the most part, which is why I'm boring, because I'm an engineer. Right? We're boring people. And the only way we can be cool is by making engineering cool. 3D printing gives us the opportunity for a kid. When my daughter, when I came home and exposed her to 3D printing, she just started making all kinds of stuff. The thing is cheap. It's $600. It's not cheap, but it costs $600 at Best Buy. You bring it home, and the kid plays around. Next thing you know, she makes a car. She makes it. That idea of touching and feeling. That's the advantage the iPhone has. You can feel it. You can touch it. My 2-year-olds, I have twin boys. They now go to the TV screen, and they're trying to change the channel because they're rubbing the screen. Because they spend enough time now playing with their iPhone, they believe that everything that's a screen has to be touchable. Daddy, it's not moving. I'm like, get the flick. Don't just do this. So because they can feel it, they connect with it. Having students feel what they're designing is where you start making the engineering profession cool and making it attractive. I talk about commoditization of skills. Education is also being commoditized. Everyone has heard about the MOOC, where you can do massive online training. You don't have to physically be somewhere. The idea that you have MOOCs in Kenya, Rwanda, and other parts of the world where the professor sits at Harvard and does an educational course, that's all great. But I also said to some of those folks at the Khan Institute, I said to them once, I said, you need to put 3D printers, those schools in Africa. Because if those kids, they don't have the luxury I had. When I went to school, times were different, and we could wait to leave Africa and come to the States or go to Europe and learn how to use a computer or learn how to use a microscope. You can't afford that today. Sadly, there are many parts of the U.S. where students have the same dilemma like the ones in Africa. They don't have access to those things, right? 3D printer will start giving students this feel, this advantage of understanding and touching what it is they're designing. Data. So what's interesting about big data and analytics and computers is that it generates so much data. But how many engineering schools today are teaching students data engineering? Right? Because I call data the multi-microscope. Because that's what you're going to use to discover new things. In fact, every lab you go to now, in a chemistry lab, biology lab, they have the microscope connected to a computer. So you're collecting all this data, but do you train the students to be able to understand and harness the data and analyze the data? So being able to create that human-computer interface for the students so that they can easily understand what it means. So let me close with a few thoughts here. So coming back to what Paul talked about, the idea of, from an energy system perspective, we see it, engineering is all about the water, energy, food nexus and climate nexus. And so bringing it together. I mean, he said every utility or every organization has a chief sustainability officer. That's true. So they have a chief sustainability officer or a chief environmental officer. They now have a chief information security officer. They have a chief cybersecurity officer. They now have a chief resilience officer. All of these things are engineering-related professions because it involves resilience, which involves building something. So thinking about how you align the engineering courses to the needs of not just society and consumers, but what the business needs and what the policy needs. Because I have to tell you, engineers have one problem. We build stuff, we build it great, it works well, and then the policymakers and the lawyers come and tell us how to run it. So it's almost like back in the day, like in France, all the generals were engineers. In fact, to be somebody in France back in the day, you had to be an engineer. Today, to be an engineer is to be nothing. I'm not kidding. I mean, it's like I struggle. I mean, even today when I go out in the field and meet people around the world, their first thought is because I'm from EEI, they think I'm a lawyer. Because we have many lawyers at EEI. It's policy, right? And I said, no, you're not an engineer. Why? Why? You don't carry yourself like an engineer. How do engineers carry themselves? Well, you're not that boring. You know, you joke around. So there's this deep perception of our profession as being all of what is not. This is not boring. It's just that we don't know how to tell the story, right? We're not good storytellers, right? And you notice that when you ask students in the engineering school, who's your best teacher? You can do the survey and find out how many times that best teacher will be someone from the engineering department. It's almost never. It's always the guy from the communications department, the business school, because they make it real. They try to take it from the abstract to the practical. So being able to align the education to these things, I think, is going to be key. Flexible and adaptive educational structures, we've already talked about that. This whole idea of interdisciplinary, transdisciplinary, multidisciplinary. And then the content. And I want to just spend a few minutes on the content here, because most STEM programs, now, I didn't know about MESA until I met Dr. Brace. Now I know there's something called MESA, that these programs focus a lot on math and science, which is great. But I think we need to start thinking about art and history. When you read history, it fascinates young people to realize, how did they build the Hoover Dam? I mean, just think about the Hoover Dam. That massive dam that has been there for almost, 50 or 75 years. Just think about the amount of engineering that went into keeping that much water behind a dam for so many years. But if you don't read history, I would love every engineering profession to have a course to have the history of engineering in that curriculum. Because you can learn something. If nothing, you can learn the mistakes that were made in the past. Like the mistake that was made with the shuttle, the space shuttle that went down. That was an engineering mistake in terms of not listening to what's happening as a team. Art, psychology, business, studying about the future. And the last thing, I don't know how you teach this, but this is something I try to spend a lot of time with my kids on, is listening and observation. How do you teach students to listen? Because you talk about the distraction, Paul, that's the distraction. They're not listening. And in this noise, how do we make MESA relevant? But I can guarantee you, if all of a sudden MESA programs had something about teaching students how to listen, parents will be a bigger supporter. Because parents are struggling to get their kids to listen, right? And observation. Spending time out in nature. I love your slides when you show the leaves. Right? I knew more of the leaves, not the birds. I could maybe, might review my days in Sweden, but I knew the leaves, not because of the marijuana. But I mean the leaves. Just understanding hibiscus leaf. What is a hibiscus? Most kids don't even know what hibiscus leaf looks like. They drink the tea. They can tell you hibiscus tea, but what it comes from, no idea. So listening and observation, modernizing the techniques. We've already talked about that. So 3 slides to end. One ties into what Paul said. So I think in the future, I would love for engineers to be more generalists, more polymath, instead of monomaths. And we have, the greatest polymath that ever lived was Leonardo da Vinci. But there are other polymaths that most people don't think about. Benjamin Franklin. He was involved in so many different things. George Washington Carver. He was a polymath. Ada Lovelace. There was a woman who actually invented the very first computer. She wrote the very first computer software. Most people don't know that. But you know what she was? She was a linguist. And how did she write it? Because Charles Babbage, who developed the first computer here in Philadelphia, Lovelace was married to a rich guy, and she was bored at home. Maybe a lot of bored people marry to rich people today. She was bored at home, and so she decided to communicate with Babbage and send him a letter and said, I've heard about your device, your counting device, which is what it was then called. I have a way to write a language that will make it understood or understandable by the average person. So she actually wrote the first computer software. We did not know that until somebody at the DOE a couple of years ago did some research. This woman had never received the credit. We all thought that the software was developed by men. No, it was a woman. And most people don't know that, right? And then Archimedes, he was also a polymath. So training engineering students to be polymathic in their thinking, to just read and develop this curiosity, brings us to systems thinking, which is where I think as an organization, if there was anything I would say, if you could convert the S in MESA to systems thinking, that's where I think the future lies. Getting students to stop thinking in silos. And I was told of a project, a robotics project done by Notre Dame, where they bring all these students together and compete on robots. And they've designed a robot that plays soccer, a robot team that plays soccer with each other. The amount of systems thinking that have to go into those projects, incredible. But the teaching should be one that it shouldn't only be for the Notre Dames and MITs of the world. It should go to every student in engineering and science across the country. Whether you're in a minority school or underprivileged neighborhood, that systems thinking has to be there. And it requires changing how even the teachers think. So I'll stop here, and I'm sure we'll have questions. So thank you.